Okay, I can't see anybody else appearing at the moment, so we'll just get started and hopefully people can catch up. What I was actually going to start with was just a quick recap of specifying options in script versus specifying options on the command line, and the difference or not between those things. So let me show you the example script we had again. So when we first submitted our command without all the sbatch options in, we did something like sbatch minus partition was standard, etc., etc., etc. Okay, so we were providing these command line options to sbatch to tell it what partition and QoS to use and things like that, and reservation, all those sort of things. And time, you could also do the same with time and with number of nodes and all those sort of things. When we move them into the script, these are exactly the same options. So any option you could specify on the command line to sbatch in this way, you could also put in a script using this hash sbatch option. Okay, and they do exactly the same thing and behave in exactly the same way, whether you put them on the command line or whether you put them on the script. There is an order of precedence if you specify them both on the command line in the script, which one takes precedence. My feeling is, or the way I remember it, is that the whatever you specify on the command line beats whatever you specify the script. So you've got a script where you specify QoS equals standard, and you did on your command line QoS equals short, then the command line would take precedence. But the reason you do them in the script rather than on the command line is usually to save typing. But the other good reason for doing it in the script is it gives you a good record of the options you specified. You might actually want to go look back. You submitted quite a few jobs, you go away for a few days, you come back and look at the answers, and there's something different between them you don't quite understand. You can go and look at the script and see what options you specified and whether there was a mistake there or an error there or something like that. So I mean, I think in general my recommendation would be always to put them in the script, unless you had a good reason not to, because you're maybe just doing something, a quick test or something like that, because it keeps a good record of what you're doing and actually saves you a lot of typing as well on the command line. But they are exactly the same things, and they do mean exactly the same thing whether you specify them on the command line or in the script themselves. Okay, so where we got to, we got most of the way through the scheduler section. Got a few little bits and pieces to tidy up at the end of that, and then we'll move on to the next bit. Of course, as well as submitting jobs, you might want to cancel a job. I submitted something and that's a mistake. Okay, or I thought, oh, I've done that wrong. I realized I got a typo in my script just after I've typed Q sub. So you might want to be able to cancel your job as well. So we could do that as well with the scancel command. So let's quickly submit this script again. This one's going to sleep for 220 minutes. Oh, it's only got 30 seconds in the time though, so let me update the time. So it actually sets the queue for a reasonable amount of time, so it gives me time to kill it. So instead of that, I'm just going to give it, say, oops. Sorry, I usually use VI, so I have muscle memory for the VI editor, which is why you keep seeing weird characters appearing in my when I'm typing. Right, so now I've updated my script, so now it should run for 2 minutes. It sleeps for 120 hours, so it's not actually doing anything useful, but I just wanted to demonstrate it being able to cancel a job. So let's submit that to the queue, and then we can do SQ minus U. And if you can't quite bother typing your username, there is an environment variable that's automatically set with your username in it, which you can use if you want. And then you don't have to remember your username and type it. So you can see my jobs there running away. So I want to cancel that job, so I can use scancel. And then you give it the job ID, which is the unique identifier for the job here. And you get nothing back, but if I run the SQ command, you can see the job's finished. You can also use scancel. So if I let's submit the jobs again, I'm going to do it a few times. So I should have now 3 jobs in the queue. And I wanted to kill all of them, so you realise there was a typo in the script for all of them. I could do scancel -u, and then my username, which is ARCHER2. And then the CG state, which means they're just being killed. But it just takes a while for them to disappear from the queue, and then they're all gone, like that. One useful thing, you've seen that I can submit the same script multiple times, and actually, it's worth noting that then if I go and edit the script file, the example job script file, after I've submitted the job, then it doesn't affect the job I've submitted. And when I submit the job SBatch, it takes a copy of the script to somewhere else where I can't edit it, so I can't mess it up. So if I then edit the script and resubmit, you get the new job script, and it won't affect the original job you submitted. So that's cancelling jobs, which is pretty straightforward. The only thing, the only slightly weird thing when you cancel jobs, or potentially slightly weird thing, is you don't get any output back to say that it's successfully cancelled the job. It just, if you don't get an error, if I try to cancel a job that doesn't exist, then I should get an error back, or a job that I don't own. They just pick a random number. Oh, okay. So it doesn't give an error at all. It just doesn't. Okay. I assumed that would give an error, but I was wrong there. Obviously. Okay. So you don't get output back from scancel. So and we talked about cancelling results. So there are some other types of jobs, one of which is very important, which we'll move on to talking about submitting parallel jobs. Everything we've been doing at the moment has essentially been serial. It hasn't used more than one core. So we're going to go on to look at submitting parallel jobs. But there's a couple of things I want to touch on first before we go on to look at the parallel jobs. So one of them is being able to just do a quick run on the compute nodes without having to write a script. Say we just wanted to run a single command on a compute node. Oh, thank you, George. That's useful to know. So if you want to put from scancel, you can add the -v option to make it verbose and tell you what it's actually doing. That's a useful thing. I didn't know that. So say you just wanted to run a command, not a script at all. You just had either an executable command you wanted to run, or a command like hostname, or something like that, which you wouldn't want to do. Instead of using sbatch and the job script, you can use srun and the command. The downside is because you have no job script, you can't put all of your options in a script, so you're going to have to type them all out on the command line. But if I did, for example, this command here, I'm just going to copy and paste it, save me having to type it all. That's srun, partition standard. Srun takes the same options to a first approximation as sbatch. QoS standard, our reservation that we're using, and I've given it a time limit of a minute, and I'm going to run the command hostname. And it comes back with nid 001001. Okay, so that command actually ran on the computer. That could be useful if you just want to run a quick check that something's working, or whether something's available on a compute node, or what is there, without having to write a whole script to go through it. But it does have the downside that you have to type everything on the line, or on the command line, to make it work. Okay, so what that does is it's a combination of submitting the job to the queue and then running it on the compute node with no script involved. And also, you may at some point find yourself wanting to actually get a command prompt on the compute node itself, so you can type the commands interactively on the compute node. You can do this as well using the srun. We've just seen which one's a command, but then you tell it that you want to run this bin bash with the -pty option with the terminal, with the sudo with the terminal option. So let me copy and paste that. Okay, so it said it was really short, but you can see my prompts changed hopefully to the compute node I'm on. Because the file system shared, everything's still here that I could use. Everything's still here in terms of data, and I can type commands and look at how many CPUs there are and things like that. So here you can see there's it tells you a bit about the CPU. If you type ls CPU and all those sort of things. This can be really useful if you're, for example, debugging a script or a program, or you want to run a few things, or you're testing a workflow and you want to test a few things interactively. before you write the job script to do it. You can sort of prototype what you want to do actually on the compute node. And then once you've finished using your compute node, you can go back to the login node with the exit command. And you can see my prompts changed again. What is minus PTY? I always say that, so it specifies the terminal. I'd have to look up what exactly PTY stands for. Maybe one of the helpers knows off the top of the head, but it specifies what shell you want to come out in the interactive job. So in this case, we want to come run in bash. Let me have a look and see what it actually says in the manual, because it's probably better explain it than my garbled instructions. So there you go, execute task 0 in sudo terminal mode. It gives you a sudo terminal, which is the terminal is the place where you type the commands, and just gives you task 0 on that in that terminal, which means that because Slurm is set up for parallel jobs, we'll discuss that in a minute. Task 0 is sort of the first process, the first task, and means you can actually use it to do some work. Okay. What happens if you don't specify? Well, let's try it and see what happens. That's useful. So if I just try and give it the command instead of the sudo terminal. Okay, so what happens is it just sits there and does nothing. Okay, so it doesn't, you don't get the command prompt back because it's not a terminal. So you're just getting a non-interactive bash shell. It's running the bin bash command and waiting for some sort of input or something like that. I could kill this with Control C. Okay. So if I Control C it, then I get back to my original prompt. Okay, so those are two specialist type of jobs that you might want to use, running for a simple command using srun, or getting interactive access on the compute node to the bash shell of the compute node using srun. Let me go back to the start here. Now, one of the key things to realize about HPC systems, and we haven't really discussed this in huge amounts of detail yet, is that although the processors are generally more powerful, you have more memory available per node than you would on a standard laptop computer, actually the majority of the improvements in performance, or the potential improvements in performance, comes from doing things in parallel. Okay, so using multiple CPUs simultaneously to get the speed up. So instead of using one core or one CPU to do the calculation, using 2 or 4, 8, up to 100,000, whatever you want in parallel. That is where the power of HPC comes from, rather than the cores themselves, or the the individual bits being faster. They cores themselves, while probably a little bit faster than the pieces, the processors that go into laptops and things like that, aren't that much more powerful, really. It's the fact that you can use lots of them together that gives the power for HPC. So one of the key things when we're running jobs, and we'll talk about this later on this afternoon, to get the performance, is to run things in parallel. So we need to know what that means in terms of submitting jobs and using the HPC system. So to do this, when you're running your programs, there are a few different ways people run in parallel. One is there's the trivial sort of parallel way of doing things, which is, I just run lots and lots of copies of my serial program, workflow, script, whatever it is, and just run lots of them because they're all operating on independent pieces of data. That's a really common use of parallelism. The other one is my program itself is written to be able to be executed in parallel, often using something called MPI, or the message passing interface. And that does just what it says on the tin. It's a way of passing data at runtime as processes running between the different processes that are running, and to be able to write parallel algorithms and speed up things by doing things in parallel. And sorry, many of the and one of the key parts of the batch system is being able to reserve multiple nodes and multiple cores for you to use, and then to be able to launch your program on all of those cores or nodes simultaneously. So typically, the way this works is you write a batch script that asks for the resources, number of nodes, number of cores, number of cores per node, and all those sorts of things. And then you have a special parallel launch program that's sometimes called MPI run, sometimes called MPI exec, can also be called srun, which is what we'll use here on ARCHER2, where it is built directly into Slurm. And you've already seen srun in running interactive jobs. I'll try and explain that's like sort of wrinkle complication. And you sometimes see AP run as well. And often you may have to specify how many processes to use in parallel, as in the script or as an argument to the parallel launch program, and how many parallel processes to launch on each compute node. And then some extra maybe commands and arguments that our program itself takes. Okay, so we're going to delve into this more detail later on in this workshop when we go and look a bit more at how we use resources efficiently. But to start off with, we're going to have this script here, which runs a simple parallel MPI program that's already installed on ARCHER2. And what it actually does is sharpen a fuzzy image. I'm just going to go through each bit here and explain it, and then we'll run it and look at the output. So these bits you've seen before, okay? Oh, the reservation's missing there. That's a mistake. I need to put the right reservation in. But we've got the hash bang, as it's called, which specifies the scripting language using, bash in our case. We've got the partition, the QoS, these options, all these options to sbatch, the reservation. Now the new ones we have here are these two here. The one with -- nodes says, give me a single compute node. And the second one with n tasks per node says, give me 16 cores on that compute node, okay, to run my program. Then we have these things with these module load commands. We'll talk about those in the next part of the course, what those are actually doing. They're making the software available, essentially, that we want to run this sharpen program. Then we use the copy command to copy across some input data from this environment variable and then the file that points to a path, and then there's a file fuzzy PGM. We'll copy it to where we are here, and then we use the srun command in our job script. Okay, there's two options here, which I'm not going to talk about very much right now. Add the name of our parallel program we're going to run. Okay, so let me put that script in and save it on ARCHER2 itself, and we'll run it and see what happens. So I'm going to do nano parallel job. I'm going to paste in the script, and the thing that was missing I noted was the reservation, so I'm going to put that in correctly. It was TO28_180, I think. Yep, there it is there. And we're going to ask for, it's going to run for 5 minutes. One node, 16 cores per node. We're going to make the software available. We're going to copy across some input data, and then we're going to use srun to launch our parallel program. Okay. So I'm going to save that. Okay, so there's the script saved. Okay, well, Christian, I'll talk about where the environment variable is defined. There are quite a lot of environment in a bit, but there are quite a lot of environment variables defined by default on a Linux system when you log in. We've seen some of them. So pwd was one we saw, $pwd, which is the current working directory. There's also, we've seen user, which specifies the username, $user, and we've seen, and there are other ones such as $home, which specify the home, where the home directory lives and things like that. This one, sharpen_input, is actually defined by one of these software modules, but I'll talk about that in the next section if that's okay, and hopefully that'll explain it to you. Just accept that it points to the location of where this data is for the moment, for the purposes of this example. So now we're going to do sbatch, our usual job submission command, and then the name of the job script. Okay. And so if I do sq $user. Oh, it's finished already. In fact, this is one problem with Slurm, is you accumulate all these Slurm output files, and it can be hard to work out which one was from the last job. I mean, it should be the highest number, but there we go. So let me have a look in the Slurm 304 5.out. Okay, it just ran very, very quickly. That's what happened there. So let's have a look at the Slurm output from that job. Okay, so there's some bits at the top about it loading EPCC job env. That's to do with this module load EPCC job env here in our script. And then there's some information about it running on lots of core, on a number of different cores. Actually, only 15 of them, which I don't understand. It says it's running on 16 processors there, but I think there's a line missing from this output somewhere. There's an error, maybe an error in the parallel program that doesn't quite print out all the processes. They're all running on the same node, and although there are only 15 of them here, there are 16 in total because it says there, because we asked for 16 here. It tells you what the name of the input file is. It tells you it's an image of a certain size. And then, oh, there you go. There's the other output. It's here. There's the other. It's just out of order. And it tells you it's doing something. It's finished. It's written some output file, and it gives you some statistics about how long it ran for. Okay. So what this has done is it's run this sharpen program and used 16 cores to implement the calculation rather than just running it in serial. And you would hope that that would make it run faster, okay, because that's what you're trying to do here. A word quickly on these two options here, the hint no multi-thread and distribution block. Those environment variables are specific to, well, there's standard Slurm ones, but they're used on ARCHER2 to make sure that when Slurm places the processes using the srun command, the parallel processes, it pins them to the right cores on the compute node to get performance. So they're not all trying to run on the same core and competing with you. They use separate cores on the compute node. Okay, so our parallel launch program in this case is called srun. Number of parallel processes per node. This is 16. Not NTAS per option. The total number of parallel processes in this case is also 16 because we asked for one node and 16 processes per node. Okay, and 1 times 16 is 16. And our program and its arguments, it doesn't take any arguments. The program is just called sharpen mpi.x. Somehow the name of the input file and name of the output file are hard coded into the program itself. And then we launched it using the standard sbatch command. Oh, and if we look, we should see also that there's the fuzzy PGM, which was the input file, and the sharpen PGM, which is the output file. They're actually image files which you can view if you log into Archer in the right way with a graphical output. I'm not logged in with the graphical output at the moment, and it's not really that interesting actually to look at the different program. The key thing is it does some work. That's all. So you've seen this job submission script. Can you all have a go at this exercise here, which is that change this job submission script from the one given above to use all of the 128 cores on one ARCHER2 node. Each ARCHER2 node, compute node has 128 cores. I know when we list them before it said 256, but they have 128 physical cores. If people are interested as to why it shows up as 256, I can explain that, but it's not very interesting, really. But try copying across that job submission script, writing it using and changing it to use 128 cores per node, run it and check that the output does indicate that 128 cores are actually being used in parallel for the calculation. You can also see here that the calculation time and the runtime were given here for the 16 cores. It should be faster for 128 as well. Okay, so we're at just after 5 to 2 now. So I'll give you probably maybe 10 minutes to get, 5 to 10 minutes to get that one done. So we're trying to finish just before 10 past 2 on that one. If you have any questions, please just let us know, or run into problems, please just let us know, and we'll try and help out. The one thing I did promise I would talk, let's say a little bit on, that I realise now, is the use of srun in both the job script and out with the job script when we used it just to launch the job. Srun has this dual use. It can be used to sort of submit and run a command, but it can also it could also be used, or it's also used to do the parallel launch within a job script as well, to ensure that you launch all the cores. So it has this sort of dual personality. In the majority of cases, people use it within a job script to launch report the right number of to launch the program across the right number of processes, but it can also be used to launch things directly from the command line. So Cameron's asking, can you specify the output directory? So yes, you can. So not to that program. That program is not written to be that flexible, but you could modify the script to either move the output after the program had run to somewhere else. You can also add a option to sbatch that specifies where standard out goes anyway, which is the stuff that goes into the slurm -job id.out file. You can redirect those things, but if your program specify, and I should specify different output directories, you can press the options to do that. Yeah, you mean the slurm file? Okay, yes, you can. There's an option to slurm to do that. Let me find out what it is. Can't remember. I think it is. It might just even be .o minus o. I have to say I don't redirect the output that very often in that way myself, which is why I don't know it off the top of my head. There you go. So you can see that it's either -o and then the file name, or -- output equals and the file name. And you have some options to add these % characters for to add different patterns to the job name based on the job. So for example, %j is replaced by the job ID in the file name. Okay, so the standard output file name is slurm-%j.out. If you've already managed to get the 120 cores one node, you can go on to the next exercise here as well, which is modifying again to run on 2 nodes and 16 processes in total, but only use 8 on each of the 2 nodes. Okay, and you should be able to see in the output that the 8 ran on each node. That 8 ran on each node. I'll give it 5 more minutes and then I will work through the solutions to these and check that everybody's happy with what that means. Okay. Why .slurm rather than .sh? So, okay, sorry, I didn't mention that change of extension. Partially because it's not significant, right? So, unlike older versions of Windows, I don't know if the same is true of new versions of Windows, because I haven't used Windows for a very long time now. But the extension has no meaning, really, in Linux or Unix. Okay, it's a thing there for convenience and for to help you identify by eye what type of file, what's in the file. You know, the extension does not mean anything, and so it could be anything. So in the example job.sh, we started with it being called something.sh because it was because we executed it like a shell script, and .sh is sort of an accepted standard for executable shell script. Okay, it just stands as short for shell. But it could be anything else. Even it could have been .bash, could have been .shell. It could have been anything like that. And I haven't been consistent in writing this material here, and maybe I should have just stuck with .sh. .slurm here is just a way of indicating this is a Slurm job submission script, but it could be a executable .sh script as well. So it could be .sh, it could be .slurm, it could be .pbs, it could be it could be .script, it could be anything. It's a personal choice. In some cases, there are sort of standard accepted standards which give you an idea, like .jpg usually indicates that it's a JPEG file, or .png indicates that it's a portable network graphics image file. .txt indicates that it's a file containing text data. But in other cases, like Slurm job submission scripts, which are less widely used, there's less of a convention about what they have as their extension. Okay, so I see you've got Debanjan. So that means that that job submission script isn't there. So if you ls in the directory, the job submission script you're submitting has to be there. So sorry, I gave mine the wrong name as well here, which has confused things. I've called it parallel job. Let me move that. So move it to the name that's in the documentation, because I've just made it more confusing by not using the right name. Oops. Okay. So now I have runsharpen.slurm like that. So that file has to be there when you do sbatch. So if I did now sbatch parallel job.sh, which is what my original script was called, which isn't there anymore, I get that same error because that file doesn't exist. Okay, so that indicates that that job script just isn't in that directory, or isn't where you specified it. Okay, and let me put up a poll just to check where people are up to before I go through the answers. So just so I can get an idea about how many people have managed to get to that stage. It's okay if you haven't. Just tell me no, because I do want to know where people are up to. Okay, so I can see that 5 people. So Salah's asking, is the most recent job always the biggest number of Slurm? Yes, because it just assigns numbers sequentially. So it's just going to keep assigning numbers to whatever the next job. They might not be, yours might not be in sequence because other people might have submitted jobs in between you submitting jobs, but it will always be the highest number. Okay, so some people seem to have managed to at least to get to there. There's no feedback from some people as well. So let me quickly go through the solutions to this. So where were we? So I've actually renamed it run sharpen. So that's the one that ran 16 tasks per node. There's the change to run on 128 cores is hopefully pretty straightforward, is to change this number to 128 here. Okay. And let me submit that. Okay. One other quick useful thing to tell you is if you put an exclamation mark and then type some letters, it'll repeat the last command that began with those letters. So if you want to run the SQ command again, you can't be able to type it all with the user. You take exclamation mark SQ, that will rerun the SQ minus user. It echoes back to what command it's pulling out of the history. That's one that can help make things a bit quicker.
We talked to people about using Control R and then starting to type the command yesterday.
Oh, okay. Yeah, that works as well. The reverse search thing as well. Okay, so hopefully this one is the most recent one, and you can see it ran. Hopefully somewhere there's a rank 128 number in this list of numbers. Some of it will be a rank 128, but it has used 128 processes, and it has run faster than my previous one. In terms of the one that uses 2 nodes and 2 nodes and 8 processes per node. What am I typing code for? So I get confused with my editors. We'd want 2 nodes and then 8 processes, not 88, 8 processes per node. And let's submit that one. Yeah, that's so Luke says he's also set up an alias for SQ minus user. I do exactly the same thing on my standard Archer account. I have alias SQ equals SQ minus user, so I can just type SQ and get that without having to worry about remembering the exclamation mark or anything like that. So this is looking hopeful because it's running across 2 nodes here. You can see you've got 2 node IDs in the node list. And let me cat the output. And so this was running on 16 processes, which sounds right? 2 times 8 is 16, I think. Even my maths, even my mental arithmetic can deal with that. And it talks about ranks 1 to 16. And you can see there are 2 different node IDs here. Okay, so it's run 8 of them on one node and 8 of them on another, according to the specification in the job submission script. And that's the error. That's what you say here. So that's quite a long section, the section on the schedule, but the schedule is so key to everything that you do on an HPC system, because all access to computers is controlled through the schedule, that we really cover it in quite some detail, and it's worth understanding what the job submission script is, how you do things through the schedule, and it's just a job submission script. It's just a shell script with a list of commands, but it has these special extra decorators that allow you to be able to specify the options that you want for the job, and getting used to manipulating the schedule and checking how things are running and things like that is a key part of learning to use HPC systems. So I'm going to move on to the next section now. Is anybody else, are there any other questions on the scheduler before I skip on to the next section? Or if you don't have any right now, that's not a problem, because if you think of something, please just ask anyway, even though we're in a different section. I'll do my best to answer it. So what's the picture? It was a picture. It's one that my colleague David Henty got, who originally wrote that Sharpen program for EPC training. It must be, it's a long time ago now, he wrote that piece of code. And he found a fuzzy image on the internet to use for it, and contacted the person who put it up there and said, you know, okay, we use this as it's example, so it's random picture of the, it's random picture of the, it literally is random picture of the internet, where we contacted the person who put it up and said, you know, are you happy for us to use this image in our training? And they said, yeah, that's great, go for it. So it's nothing specific. There used to be an example which had Mel Gibson as Braveheart as the blurred image, but that was subject to copyright from obviously the studio that produced the Braveheart film, so we couldn't use that anymore. Anyway, okay, so one of the things that came up was questions about environment variables and where they come from and how they get set and things like that. And we're going to cover that in a bit of detail, a little bit now when we talk about accessing software via modules. So one of the challenges with an HPC system, I think, is that there's lots and lots of users with lots and lots of different demands and lots of different types of software. Okay, it's not like it's your laptop where you have a setup you want to use, and actually, that's more and more of a problem for people with their own laptop, is they want to be able to have lots of different software stacks anyway. It just so happens that on laptops and our local systems, we deal with that in a different way. You know, if you use Python, you may have used virtual environments or Conda environments to make different software stacks available. Or you may even have used things like Docker and these sorts of tools to be able to use containers to give you different software stacks. On an HPC system, we've got that problem compounded because you have thousands of different users all wanting maybe slightly different versions of software, or are installing software that has different compatibilities. Now, you can use some of the solutions that you would use on your laptop to solve those problems, virtual env and Conda environments, if you're using Python, for example, and containers, if you're using containers, but traditionally they weren't available on HPC systems, so people had to come up with a different solution to make different software available, make sure it didn't clash with each other, and allow users the flexibility to load different versions of the same software on the system and have them available without them causing all sorts of problems. So the solution to this was what was called software modules. Okay, on most HPC systems, they use these software modules to make these different types of software available. So, and they may have, everybody might have slightly different competing demands, or they might have slightly different dependencies, and the software modules can express those dependencies as well. So, a module on the HPC system is a self-contained description of the software packages, and it contains the settings required to run the software package, and often encodes dependencies on software. But the way it does this goes back to the question we had about environment variables. The way it does this is by setting environment variables. Okay, so what software modules do is manipulate environment variables to make different pieces of software and different versions of software available when they're loaded. So let me show you an example to try and make this more concrete. So let's go back to, so we're back on ARCHER2 now. And I could use the module avail command to show what software modules are available. And there's quite a lot of them on ARCHER2. So we get a scrolling list. And then there's separated into different groups as well. So for example, there's this lot here at the bottom are in module file CSE apps. These are typically applications. This one's CSE libs. These are typically software libraries. CSE utils, typically software utilities. Okay, so for example, an application may be something like material science modeling software such as VASP, or I've mentioned GROMACS before for biomolecular simulation, or OpenFOAM for computational fluid dynamics and things like that. Libraries may be typically things like I know we've got Hpc for solving equations, and various other bits and pieces, MKL, which does dense linear algebra and things like that. And utils are things like CMake for building software, potentially some other things that you may know, matplotlib as part of Python for plotting graphs and things like that. GNU plot for the old-fashioned graph plotting people among us. Okay, and each of these is a package that manipulates the environment to make that software available for you. So, and there's plenty more. There's some supplied by Cray as well, because HP Cray, because they make the system. So scrolling down with space, and then finish there. And you can also show the ones you currently have loaded. Okay, so they're all the ones that are available, but some of them are already set in my environment, and that you get that through the module list command. Okay, so these are the ones that are loaded by default when you log in to ARCHER2. Now, some of these might not make, I mean, the names generally possibly don't make sense to people, and some of them are just for manipulating environments and don't actually load software really. But key ones here, for example, this cray mpitch loads the MPI library, makes the MPI library available. This module here, CCE, is the cray compiling environment. This will make compilers available, like C compilers and Fortran compilers for people building code on the system. And what you'll see is that actually, for example, none of these are, sorry, not all of the modules available are loaded, right? So when we want to access a piece of software that's not in our standard list, then we need to load it to make it available. So let's have a look at one to use, say, there's a netcdf, which is a type of data format. There's a utility called ncdump. And let's see if we can find it. So the command would be ncdump. Okay. And it tells me the command's not found, and I can see where it's searching to look for a command. Now, remember I said that everything in Linux or Unix was a file. That means all the executables are files as well. And this thing here, this long string, which is a list of paths all separated by colons, you can see here there's a colons in between, is known as the path. And it is an environment variable. Path is something that is set by default for you. And it says, look in these directories for executables. And you'll see that path here matches exactly the path that it was searching in for ncdump. Okay, so it says, here is the list of directories to go and look and see if you can find an executable when somebody types a command. You know, so if I type which Python, where is it finding Python from? It's finding Python from user bin. And in path somewhere there it is there, there'll be user bin specified as somewhere you should go and look for software, for executable software. So the ncdump command is part of the netcdf module. So we can make it available by using module load cray, because it's supplied by cray, not because it's a cray thing, but they provide that module load cray netcdf. Okay, and now we can do, okay, and suddenly it can find it. And how's that happened? Well, what it's done is it's changed our path. So if I echo path again, the environment variable path, you can see that now it has this additional entry at the front of it. And that's where it's finding the ncdump executable. So what the software module actually is doing is manipulating our environment variables. So when we're asked, you know, where does this sharpen location come from? Where did we use that environment variable to copy data across? That was set by the module. So let's look at the sharpen one. So if you remember from our job script, in fact, let's look at our job script. Okay, it was called, the module was called training sharpen 1.0. Okay. Okay, so it lists it there. If you give module avail a module, it'll list all the matching ones at the start. So, you know, for example, if I give it just VASP, it'll list all the ones that start with VASP. Okay. But what I can also do is module show, which will tell me what that module is actually, what that software module is actually doing. And you can see the things it does is it prepends the path with this directory, and that's where the sharpen executables live. So that's how it can suddenly find them in our job submission script here, how it suddenly knows that where sharpen mpi.x is. It's in this directory because this software module is manipulating the path. But you can see it also sets this environment variable sharpen underscore input to this path. So the actual path for this fuzzy PGM is work Y07 shared training sharpen input fuzzy PGM. Okay, but we encode that in this environment variable. So all the software modules are doing essentially is manipulating the environment variables we have available set to us. If you ever want to see all of the environment variables are set on for your account, you can do that with the env command. That will list every environment, every module that's variable that's exported at the moment. You'll see there's a lot. Okay, and can be hard to interpret. So that is all that software modules are doing, is manipulating the environment variables such as our path, right? And if we then unload the module again, we can remove the module to make it not available. Cray netcdf. It's actually that's the only one loaded, so let's unload it. NC dump's gone again, and you can see that that extra directory has now disappeared off the front of the path. So when you unload the module, it does the inverse and undoes everything that you did. And as George says, you can use tab completion with module names to make it easier to type them in or to search for them. Okay, so software modules sound like they're something magic, but they're not. They just manipulate the environment variables and make different things available by manipulating path and other special environment variables, or setting just custom environment variables that ease our use of the system, such as the one we saw in here. This just saves us having to type a long path to get the input. And it means that actually, if somebody installs a new version or changes the location, they can just change the setting of that environment variable, and actually all the scripts will still work because it's encoded in a variable, not in a hard-coded path. Okay, so that's how you make different software available, and you can see actually that how that helps you with different versions of software, because if you can control the paths and which is available, then you can manipulate which actual version of the software you want to use. So let's go back to our NC dump example. So module avail cray CDF. Okay, so when I loaded it before, I got this, whatever the default version was, because I didn't specify the version number. But if I wanted the newer version, which is 4.7.3, 4.3 rather than the default version, I can do module load and specify the exact version I want. And then if I do NC dump, oops. Okay. So minus version doesn't work there. The minus v does. Yeah, minus v. No, okay, it doesn't matter. But it tells me at the bottom.
It's telling you. Okay.
It tells me a version number at the bottom anyway, and when it was built. So there's no minus version option as far as I can see for NC dump. And we decide suddenly, okay, we want a different version. We don't want the version we've got loaded. You can use the module swap command, right, which is the equivalent of then, which is the equivalent of unloading the old one and then reloading a new one. So cray netcdf. netcdf. Sorry, I'm not very good at typing today for some reason. And what version was it? It was 4.7.4.2 was the default.
I think you loaded an HDF5 variant of netcdf.
Did I?
Yeah.
Oh yes, so I did. Sorry,
You
that was because of the tab complete.
Talk at the same time.
Yeah, no. It was the tab completion, and my copy pasting was not right. Oh yeah, I copied from here. Okay. And the tab completion was getting it right. I was wondering why it was doing that. So I can do module swap that to create CDF 4.7.4.2. Okay. And hopefully, there we go. It's got the older version, not the newer version. Okay. So the modules are and as you saw there, Actually, what it's also telling me is you can't have those two modules loaded at the same time because they give you this access to the same pieces of software, and that makes no sense. So what I was saying is there's a conflict here. You can't have netcdf HDF5 parallel and Cray netcdf loaded at the same time because they both give access to the same tools and the same commands. So that would make no sense in your path. Okay, so in your job scripts, as you've seen, I'm not going to go and do this exercise because we've already done it in some sense. In our run sharpen, we loaded a module to make the software available. This other module load here, this EPCC job env, is a quirk of ARCHER2. We've had to create a little helper module to make sure that the modules are available within the job script. Okay, if we didn't have this, then you wouldn't be able to issue module load commands. And so every script has to have this to make sure that the modules are available for you to load. Okay, so as well as setting environment variables, modules can also do configuration of modules itself. And that's what this EPCC job env module does there. Okay, so modules are the solution on HPC systems generally to making different sorts of software versions and different types of software available. There are other options for doing this, particularly if you use Python and things like that, using virtual envs, Conda environments, or if you're using containers. We do have a course on containers if you'd like to learn more about that. There should be one coming up later in the summer on how to use Docker and Singularity. But there are different options, but the sort of standard way of doing things on HPC systems is still via these software modules that manipulate the environment variables to make different sorts of software available. There is a command called module purge, which cleans everything out. Okay. And now if I do module list, there's nothing available. Now on a Cray system like ARCHER2, this is a bit of a problem because nothing works without some modules loaded as well. But it says, oh, well, maybe you did this, you didn't want to do this, so you can try this. And it should put everything back, or it should put things back into the state where they're useful. And it has done something, and it has made the modules available, but your environment's still not in the right state. If you issue module purge, then generally the easiest way to fix it is to log out and log back in again. You can also do some other commands, but I don't want to go into that here because they're more related to software development rather than just using an HPC system. So I'm not going to try and confuse the system right now with that. So that's a sort of whistle-top tour of modules. They may or may not be new to you. Do people have questions on modules, or are you happy for me to go ahead and move on to the next section? Yes, George. So if you want access to modules in a batch script, you have to do you first have to load the EPCC module, the job env, I think it is, isn't it? Yes, EPCC job env module, and that makes all the other modules available to you on the compute nodes. Okay. Often, if you're using okay, so why would you need to remove modules apart from to load other versions of the same module? So one case might be that you've made a mistake when you're loading the module and you loaded the wrong version, and it wasn't the one you wanted. So that can happen on the compute node. Say you're using Python, you loaded the wrong module, the wrong version of. I know we've only got one version available, but you can imagine you load the wrong version of matplotlib and it doesn't have the feature you want. Okay, so you might need to unload it to get back to the one. Of course, you can always reset by logging out and logging back in again. One thing that does remind me, though, one thing I would caution against, quite strongly caution against, is adding module commands to your bashrc file. We said you could customize your environments by adding things to bashrc file, such as setting work. Also, maybe like there was the idea for setting an alias for SQ to shortcut. to be able to see your jobs in the queue rather than everybody else's. Those things are fine because they don't affect things in a big way. But if you put module load commands and module swap commands and things like that in your bash RC file, it can make it very difficult to debug when things start going wrong, especially if you're in conversations with the service desk and things like that, because your starting environment will be very different from what the default one is on the system, so it can make it much harder, much more difficult to get to the bottom of any sorts of problems. So I would caution against putting module loads into your bash RC file, and when you run into any problem, or if you do and you run into problems, the first thing I would do is probably comment them out in the bash RC file and see if that fixes anything. It's a good idea to put module list in your jobs. You can see in the output which modules those. Yep, that can be very useful, particularly if you're trying to find out why something's changed. You know, something used to work in the past a year ago and isn't working now. You know, if you've got the record of what modules were loaded a year ago, then you can see if anything's different, and potentially if that might be something that's different, that's stopping your program from working. So it is good to keep a record of that by putting the module list command in your job script. Okay. In practice, is there any problem with having loads of modules loaded? So no, generally not, right? But you'll find, I mean, there's only a limited number of combinations here. Okay, so actually, while it looks like there's loads and loads of modules there, actually you're often doing something very specific. So for example, a lot of the time you'll be running jobs and using a job script. Okay, so in that job script, you would only have loaded the modules you needed for the work that was going on in that job script. So it sort of naturally cuts itself down in that way. You know, and when you log in a session and maybe you're doing some analysis of data you've generated on the HPC system or something like that, you'll tend to only have the modules loaded you need for that analysis and for that session you're working in. I said I wasn't going to go into huge amounts of detail, but there are ways also to save the set of modules you have, and then you can restore them at a later date. You know, so you can, there's a module save command which saves the current modules you have loaded into a file, which you can use the module restore command to bring back out, so you can replicate the environment again without having to get all the module commands in the right sequence, which can be quite useful. You know, if you've got if you find you get to a setup where, you know, a set of versions and things that's working, you can do module save and capture that and then reuse it in your job scripts or in another session in the future. Okay, so I'm going to skip on. There's lots of information out there in modules. There is also useful information in the Archer documentation on this that's worth reading about how the software environment works. So let me show you the ARCHER2 documentation, which if you haven't seen before. If you go to docs.archer2.ac.uk, a lot of this stuff is not specific to ARCHER2. There we go. There's the dev environment one, but it's the software environment one that provides the basic information on how modules work. So I'll put that link in here as well. Okay, I mean, some stuff is specific to ARCHER2, but most of it actually is just generic information on how modules work and you know, how you could use them in job scripts and in your day-to-day work. Okay, so I'm going to go on to the next section now, and we're going to talk a bit about file transfer. And then after this, we've got this session. We'll be running more jobs, and you'll be looking at a parallel. We'll look at the sharpen example in more detail, and you get to run some more stuff in practice and work out and try and understand what's going on. So there's a few different cases of file transfer. You know, so usually we want to get data onto and off the HPC system. And how you do that depends a bit on where the data is coming from. Okay, so you may be pulling data directly from the internet somewhere. You may be pulling it from another remote computing system somewhere else, or you may be transferring it from your laptop or workstation onto the HPC system. And there's different, it's slightly different how things work in each of those cases. The first and most simple one, which we'll look at, is getting files from the internet. Okay, so there are two commands that are there's multiple commands that are useful here. Two of the most useful ones are a curl and wget. Not every system has wget, which is why we list the curl one. Wget's actually got a slightly easier syntax. So, for example, hopefully this works. I haven't tested this one. So we use wget and then give it a URL of somewhere on the internet, and it should get some data for us. Okay, so it did get some data for us. Hpc Intro Data is the test file that's part of this website for this call, for this course. Okay, other things that use this sort of HTTP transfer request are, for example, if you clone Git repositories, you can do git clone HTTPS and whatever the path to the repository is, then that also pulls data directly from the internet and saves it locally for us, so that you can see there's the data we pulled, the HPC intro data, and it has some sort of data files in it. Okay, it's just an archive file with some sort of data files in it. So what is this tar.gz? It's an archive file format, a compressed archive file format. You may have come across zip, and you may not have come across tar.gz. It sometimes has the extension tgz as well, and we'll talk a bit about it in a minute anyway. So we can also, as we use SSH to log in, we can use SCP to transfer data from our laptop or workstation to ARCHER2 itself. So if I log off system back to my laptop, and I'm going to, I wonder if wget just works here as well. Perfect. So I've got that data file now locally on my system. It's just here. I want to copy it up to ARCHER2. So I can use the SCP command, similar to the SSH command. And SCP takes all the same sort of options as SSH. So actually, okay. So SCP, I had to pass the path to my key, the public part of my key, sorry. And then I have to give the name of the file I want to transfer, which is HPC. Oops. Sorry, my typing is useless.
Andy, doesn't SCP need your private key? Your public key is at the other end.
You're right. Yep. So I've given it the private key, I've given it the local path to the file, and I want to transfer it to my username at login archer2.ac.uk. The final thing I need to do is put a colon on the end, because I want to give it the path where I'm going to transfer to. So I'm going to transfer it to my home directory, which is just tilde on ARCHER2. Let's try that. It asks me for my password, of course, and maybe your SSH key passphrase if you haven't got it in an agent already. Okay, and then it tells me it's transferred the data. So let's go SSH, SI. Oh, I typed my password wrong, I think. Okay, I did get it right that time. And there's the data file that I copied across. So Christian's asking if you could do the SCP from ARCHER2. Yeah, and George's answer is the right one. You have to be running a server that's listening for SSH. Essentially your laptop, unless your laptop has an IP address or that you could connect to directly and is listening for SSH connections, then you can't do that very easily. Is it difficult to do? Depends how happy you are. Yeah, okay. Depends on how happy you are on configuring those sort of things. On Linux, you could just run it. On Mac, it's probably pretty simple as well because Mac's FreeBSD under the hood, so be simple to set up. But the other way you could do it on a Mac or Windows would be to use a Docker container that runs SSH to transfer data. But you have to be careful on security. Yeah, I mean, you would have to be careful on security because as soon as you do that and make your system publicly accessible, then people on the internet can probe your system and try and break into it and horrible things to you.
Often if you have your files on another service, either another HPC service or some kind of data service, you can do it either way. So you can either push them from the source or pull them from ARCHER2. But you would not normally do it. You would not normally pull it from your laptop.
No. So I mean, often people have data either on an HPC system or another service local to their institution and want to move the data about, or maybe you're using a large public data set such as astronomy or climate data set that's hosted on a server somewhere where you can transfer it and pull it using some sort of file transfer. So in that case, yes. So if you want, this is where it gets a bit complicated transferring data about because different sites have different policies in terms of how you connect. So for example, if you had another HPC system and you wanted to get the data from that HPC system or another remote system, you want to get that data from that remote system that's not your laptop, that is able to accept SSH connections and all that sort of stuff onto ARCHER2. It then starts to depend on how the access to that other system works. So if the other system lets you access it with just a password and you don't need a key, then you could do SCP from Archer to that other system and just enter your password and pull the data. Okay, but if the other system still requires an SSH key in the same way that ARCHER2 does, then you have to somehow pass that key through. So you either have to have the private key on ARCHER2, which is ideally not what you want, right? Because the less places you have your private key, the less secure. The more places you have your private key, the less secure it is. Or you have to run an SSH agent that allows the connection to call back to your laptop where the key exists to check those sort of things. So it starts to get pretty complicated, pretty horrible. Or if you did the other way around, you'd have to have your key to access ARCHER2 on the other HPC system, and you're in the same sort of problem as well. But generally, especially in these days of working from home, pulling data from other systems or directly from the web onto ARCHER2 is much preferable because, especially with large amounts of data, ARCHER2 has a really wide connection into the JANET, the academic internet backbone in the UK, which then has large connections out to, for example, to the sort of commercial cloud people and also to other academic internet across the world. Okay, so you've got a lot of bandwidth there. Whereas with your laptop, you're often limited, for example, with your Wi-Fi bandwidth in your house and what your internet service provider allows you to push in terms of upload, which is often a lot less than you get in terms of download. So transferring data from your laptop when you're not plugged into a wired connection at an institution can become a bottleneck. So often you want to pull it from another server. But then, like I say, that has this complication of what credentials do you need to access the other server and how does that work in terms of having them on ARCHER2. Typically what I'd say for ARCHER2 is you can register multiple SSH keys against Archer2. So if you wanted to transfer data from another server, I'd say rather than move your laptop SSH key to the other server and then push the data to Archer2, I would create another SSH key on that server, register that on via safe Archer2, and then push the data using that SSH key instead of the other one. Yeah, exactly. I mean, doing it for your laptop, going for your laptop when you've got large amounts of data is just not. It is just painful, and right, it's a really horrible thing to have to do, especially when you're working from home and not plugged into a local wired Ethernet. So going cluster to cluster is definitely the way to go in that case, but it does have some wrinkles in terms of keys and access mechanisms. The way I often end up thinking about it is, do I have a server somewhere that just lets me access using a password and no key required? Because that makes things much easier. Because then I just need to type the password in and it's easy peasy. But when keys are involved, it gets a bit complicated and horrible. And sometimes it's just creating another key and registering it and doing it that way. But the worst comes to the worst, you just have to make a copy of your private key on the remote service too and use that. Though it's not the best from a security perspective, but it may just have to be the pragmatic way you go. But transferring data and moving data around is one of the most painful things to have to do. It really helps if somebody's set up a service for sharing the data. They know, like this is where the people who do the climate data, ECMWF, for example, and the astronomy data and the CERN people, are streets ahead of lots of other research areas in terms of making data sets available to people in a way that can be downloaded quickly. Yes, George.
I was just going to say there are some clients, I know we don't talk about them in our documentation, such as MOBA Xterm, that do make it somewhat easier. In that, if you remember when I showed my login earlier, it did pop up a message asking if I wanted to log in as SFTP at the same time. And then I can drag and drop files between Archer and my PC, and I'm already logged in and authenticated, so it just uses my existing connection.
Yeah, I mean, that makes the interface a bit easier, but doesn't solve the problem of the large data.
No.
Which is a bit of a pain. It's really tricky. Okay. So it's also worth noting that some clusters are behind firewalls. Archer2 doesn't suffer from this. We're on the open internet to make things as easy as possible to people. If there's a firewall involved and getting through a firewall, it makes things even more complicated. That is a thing to watch out for. It makes things even more complicated because, one, you have to get through the firewall, which is a pain in the neck. But also, firewalls just slow down data transfer because they check every packet on the way through, and it just throttles large data transfers. So if you're seeing poor data transfer performance from one location, it's worth checking if there's firewalls involved somewhere and whether there's quite a lot of institutions run what they call a DMZ, a demilitarized zone or a data management zone, where it's a place where you can put data that sits outside the firewall to allow you to transfer data with high performance to other places that sits outside an institutional firewall. Fine. So the only other thing to note is you can transfer directories as well recursively. So you met yesterday probably when you were, or you may have met the CP command, and you supply the -R flag to CP. That allows you to copy across entire directories and preserve the directory. You can also do that with SCP with -R, but generally it's not recommended unless you've only got very small amounts of data in the directory or very small number of files, because each file transfer has some sort of static overhead. So if you're transferring thousands of files, it can become very, very slow if you transfer them individually. And as we'll see in a moment, actually the right thing to do in that case is to turn them into an archive and then transfer the single archive file and inflate it back on the other side, because that's much more efficient in terms of transferring data than transferring lots and lots of files. So what's this slash? Well, most of this we've covered. So Nico's asking, is the limit to how large files you can transfer to Archer2 and how long you can keep them there? The answer is yes on both cases. So every project on Archer2 has a quota, a disk quota on both home and work. Separate disk quotas. They're generally much larger on work than it is on home. And you can't exceed that. So once you've blown that, then you have to delete files to make space. And in terms of how long you can keep them there, then that depends on the length of the project. Once the project's finished, I think the policy is that generally expect people to have the data off the system about 3 months after their project ends. So projects have a defined life on the system, and once your project ends, you need to get the data off the system to somewhere else, where you can store either a local institutional data store or something else that's associated with your research area. Okay. So I think we've sort of come across paths quite a lot, and the fact that the slash separates subdirectories. But when we do SCP, so let me exit again and do that data transfer again. So here when I copied it to my home directory. But if I wanted to say make use of the fact that I have much larger quota on /work rather than home, I might want to put it straight into work rather than go to home. So here I could use the I could put in the path to my work directory. Okay, and that would say, take this file that's locally, this hpc intro data.tar, and transfer it to Archer2 and put it in this directory. And / is the root directory, as I showed before, and these are all subdirectories that we can follow down eventually to my directory where I've got permission to write things. Let's do that again. Okay, so this time you don't get anything different in the prompt, but it's actually put it into a different location. It's moved it to the work directory on Archer2 for me rather than my home directory. Okay. And these paths could be. This is what's called an absolute path because it starts with a /, so it starts at the very root directory and specifies explicitly which subdirectories from there I want to go down to. There are ways you can use relative directories and things like that. I'm not going to talk huge amounts about that, but all the rules of paths in terms of relative directories and absolute directories apply in SCP as well, in the same way they do as in the CP command. The difference between the CP command is essentially that you're specifying a remote location here. Otherwise, it's entirely analogous to CP. I had obviously the extra option of specifying my location from a certificate. Rsync. So there's also a command called Rsync, which you may have come across, which is remote syncing of files. That allows you to transfer data. It generally uses SCP under the hood, but it's a bit more flexible in that it will, for example, compress things on the fly to transfer them. It will allow you to pick up your transfer through. It allows you to only transfer the data that's changed between two systems, so you can keep two directory trees in sync and things like that. The syntax is very, very similar to SCP, and then you give it rsync, the local file, and then the remote direction, a remote directory, the remote location and directory you're transferring it to. And it takes a few other options here. So often people use it with the most commonly used options are A, archive, which preserves the timestamps and permissions as it copies across. Verbose to give information on what it's actually doing as it's transferring. Z compresses the file. That may or may not be useful depending on how large the file is. And P, partial, allows you to pick up if the data transfer gets interrupted for some reason. And you could do the same with a directory. If you give it directory, then it does the transfer recursively for you, because the -A option implies this recursion. So rsync is often more flexible than using bare SCP, but essentially works in exactly the same way otherwise. Obviously, as well as uploading files, I might want to download files, so I can use SCP again. So let me get the SCP command. In this case, you just reverse the location of the files. So for example, I want to get it from Archer. So I give the Archer path first. And the file was called Hpc Intro Data .tar.gz, and I want to get it to here. And it asks me for a password again, of course. And that copies it back over from ARCHER2 to my local system. Okay, so it's like SCP. You can swap the source and destination depending on which way around you want to do things. There's a note on ports here, but that's not really interesting for this case, because almost every system you come across will have use port 22 for SCP, so you won't need to specify that. No, so the rsync minus Z, Cameron's asking if the rsync minus Z option of the files will be GZ. No, it does the compression and decompression on the fly. So the files that end up at either location have the right names and are not compressed, but the rsync command is doing the compression as part of the transfer and then doing the uncompression at the other end as part of the transmission for you. So you don't end up with different files. The minus A is the archive option. That does a few things. One, the main thing it does, it preserves timestamps and permissions. So your file, if you transferred without the minus A, then when you went and looked on the remote system, you'd see the files all appear. If you listed them with ls-l to show the timestamps of when they're created, they'd just been created. Whereas the minus A option transfers across the timestamps from the original files. Okay, so you could check which versions changed when. And the reason Rsync wants that information is it can use that to work out whether a file has changed on the remote system, with the local system. So, it could say, oh, well, this file's, I've got this directory tree existing at both ends. This file's newer at this end, so I need to transfer it back the other way to keep them in sync. Okay. So Rsync is more than just a copying tool. It allows you to sync up directories, so you don't transfer everything every time. You only transfer the things that have changed. Minus A also implies recursive, so it'll look down the whole directory tree. George says, is it possible to see how much space you've used and whether or not you're close to exceeding your quota? The answer is yes, you're safe. So if I go and look in on the ARCHER2 website, the web service where you logged in to create accounts, if I go and look at, I've got lots of login accounts from lots of different projects, but if I go and look at my login accounts here, it tells me how much of work and home I've used. And if there was user quotas, they would be listed here as well, but there aren't any user quotas. But if I look at the project T8028, it tells me how much everybody in the project is using on work and home and what the quota looks like. Yeah, the safe quotas and usage are updated once or twice a day. They might not be exactly up to date with what the system really looks like moment to moment, but that's usually enough to work out what's going on. Excuse me. Okay, so I'm not going to worry about the port thing because that's not interesting. So one thing I did want to mention, just briefly, before we stop for a break, I think, is to talk about archiving files. Okay, so one of the biggest challenges with transferring data is when you have lots and lots of files. Okay, because the reason that's a challenge is that when you're transferring data, each of those, if you do an SCP -R and say there's 100 files, each of those files is essentially a separate SCP command. So what it needs to do is establish the connection, make sure the connection's encrypted, start up the transfer the data, shut down the transfer, do that again for the next file. Okay, and that sort of established connection, startup, shutdown, transfer has a static overhead. So if you are doing that 100 times, then maybe you don't notice it. If you've got to transfer, say, 10,000 files, then that is going to be a really big overhead eventually for transferring your data. And the way to get around that sort of issue is to archive the files first before you transfer them. So that's turn your lots of files into a single large file, which then you only have that overhead once in the transfer and copy it across. And that was what we saw with this this tar archive here. Okay, so I showed before that we can look at what's in the archive with the tar minus tf command. Sorry, I should log in and do this on ARCHER2 rather than do it locally to make sure you all have the same experience. So you've probably come across archives before, particularly in zip files. Okay, zip is another way of doing archives. Just on Unix and Linux, tar has been more common over time. But you can use zip just as because the zip command's there as well on ARCHER2. So if you prefer to use zip, you could do that as well. So this shows me what's in the archive. Okay, so that lists all the files that are contained in this archive. So let's have a look at the size of this data. Okay, so it's 40 kilobytes. So the du command is disk usage. Minus S, I can't remember, minus H makes it into a human readable size format. To probably summarize. So, okay, so if the file system block size is larger than 36K, you'll see a larger number. Files cannot be smaller than one block. So, okay, so this is the block size on ARCHER2 here. Summary, thank you, George. So let's unpack the archive. We're going to use a few extra options there. X is extract, V is verbose, Z is gzip compression, and F for the file to be unpacked. Okay, so we'll do tar minus X VZF, the name of the and then the name of the file we're unpacking, which is this tar archive. So let's do that. Okay, and that has created this folder HPC Intro Data, which has all this data in. Let's do du minus sh HPC Intro Data. Okay, so it's 148K. So it's about what? Not quite 4 times larger, but something like that. Okay. Yes. So I was just going to mention that. So Cameron says, I don't think you need the Z. So that's true. So when you extract now, modern versions of tar do not need the Z to tell you to uncompress when you uncompress it. But if you want to create a compressed archive, it doesn't do that automatically. So you need the Z option if you're doing the opposite command. Okay. Fine. So if we want to reverse the process and make a compressed file, we do it in the opposite. So this time the options are C, which is create an archive, V, verbose to tell me what I'm doing, Z, because I do want to compress it, and if I don't specify the Z this time, then it won't create a compressed one. And then I'm going to give it a new file name, which doesn't exist yet, and then give it the name of the directory that I want to compress. Okay, and we should see that I've now created the compressed data tar Z, and we can look at the size of that. It's 44K. It's a bit quick. It's a bit larger. That difference is probably because it's a different version of tar being used at the two ends, from the original set to the new set that I've created here on ARCHER2. So it's not quite as good. Oh, it's not quite. It's compressed it differently. Let's say. Let's put it that way. Okay. So that is how. I mean, that's a simple way to compress and uncompress data from multiple files into one large file that's potentially smaller. Then you can transfer across and uncompress at the other side, at the other end. One thing to note about working with Windows is that if you're transferring text files between Windows systems and Unix system, Mac, Linux, or whatever, This causes problems because Windows can encode its files slightly different and adds an extra character to each line. And you can see this, what you typically see, the way we typically see it is when people submit batch jobs and SBatch complains that the script isn't valid. And if you look at the script on the system, it looks like it's fine. It usually means there's some funny characters in there because they've been created on a Windows system and then uploaded to the Linux system. And you can convert them using the DOS to Unix command. Now, I'm not sure that exists on ARCHER2. I have to say, yeah, there's no DOS to Unix, so that's just a mistake, and we need to install it to make it easy. There are other ways around it, and we can put some. There are other ways to convert the files. I'll put one of the commands. I'll look it up in the tea break we're just about to have, and put one of the commands in the Etherpad for how you can convert without having DOS to Unix available. Because it is pretty straightforward, and it does happen quite a lot. So Christian's asking, is it useful to compress the data first with tar and then rsync with -z? I would generally say no, because you're not going to gain anything very much from compressing it twice. You know, the extra CPU overhead of moving it across. So the extra CPU overhead of doing the extra compression won't gain you enough to make it worthwhile. So generally compress once. So if you can create a compressed archive, we'll look at this. There's a bit right at the end of the course about best practice, and it talks a bit about the different options for rsync and transferring data a bit more. We can look at that there. And George says sometimes it can make it bigger. Okay. I don't know, is there a reason for that, George?
It depends on the algorithm. If you compress with two different algorithms, it may be that the second algorithm is looking for lots of repetition, which it typically won't get in a compressed file. Okay. So you might end up with something. I mean, it's the order of the same size. It's effectively a zero change, but you know, it could be a little bit bigger.
Okay. I mean, yeah, it's worth noting that some things compress better than others.
Yeah.
Some types of files compress better than others. Things with lots of repetition. So some image files don't compress well at all because they're already a compressed format, essentially. Yeah. For example, text files tend to be large text files tend to be things that compress very well. For example, but it depends on the data and the structure of your data as to how well it actually compresses. Okay. So there's various different ways to transfer data. Some to get things directly from the internet. There's SCP and rsync for moving data about, but as we mentioned, it can be a little bit complex sometimes between different HPC systems and different servers, depending on what their access mechanisms are, and you end up with trouble with keys and things like that, which can make it a bit difficult.
So I put one thing in the comment. It is worth noting when you've got a tar file that you want to unpack, it is worthwhile doing a TF first, just to check where it will unpack. Many times in the past I've not done this, and I've unpacked a tar file in my home directory, and it hasn't unpacked into a subdirectory. It's just unpacked thousands of files into your home directory, and it's totally miserable because then it's very hard to get rid of them.
Yeah. No, that's a good tip, is to always check before you do it. I did have somewhere as well. I can't remember exactly where it is. I'll look it up over the break as well. There was some advice on, you know, how to verify the integrity of your archive before you delete for example, before you delete the source files. You know, so often you'll create an archive and then you want to get rid of the original data it came from and transfer it off ARCHER2 to free up space. But you want to make sure that that archive actually really does contain the data and is verified to contain the data before you get rid of this original source data. I'll look up the link for that and put it in the Etherpad again. Because there's some documentation on that somewhere on how to do that operation, because that's also a useful thing to be able to do. Okay, so now we've got time for a quick break before we go on to the last things for the afternoon before we finish at 4. So if it's okay with people, I'd just like to take essentially 10 minutes for this break. My clock on my computer says 12 minutes past 3. So if we can aim to come back for 20 past, that'll give us 8 minutes. It's enough to get tea and stuff like that, and should give us enough time to get through the rest of the material as well. If people aren't quite back by then, I'll hang on for a couple of minutes probably. But ideally, if we can get back for 20 past, that'd be great. And then we can finish the last two sections of the course, and hope we have time also to cover some questions. Okay. Okay, thank you everybody. So I'll put the time in the chat, and I'll see you hopefully in a very short while. Okay, I'm going to get started. So the last two sessions are, we've got one on how to use resources, measure the resources you're using, and then a quick section at the end just with some sort of tips and best practice on HPC systems. And one thing I should say with all of this stuff is you won't lose access to ARCHER2 at the end of this course, so you can carry on using it at the end of today. You know, you can carry on using it for another few weeks if you want to practice with the examples here in the course again and go through them in a bit more detail, or you want to try and run your own things and see how they work. So you can carry on working on that. And we'll also, in a couple of weeks' time, we'll run a session where you can come and ask any questions that you've had on the course, either you thought of after the course or in the process of carrying on using ARCHER2 and practicing things with it. So don't worry too much if you don't get through everything, or you feel like you still want to have a go at things. You've still got the chance to do that and the chance to come and ask us questions about that later on in a couple of weeks' time. So we've covered most of the basic skills of using an HPC system now. So that's logging in, transferring data, looking at accessing different bits of software, and using the scheduler. Okay, so but one thing we haven't covered really is how do you estimate how much resource you might need? How do you choose those input parameters for your job scripts? Number of nodes, length of wall time, number of cores per node, are all those sorts of things. Where do you get those estimates from? And the answer is, well, benchmarking or asking people who've done it already before are the two obvious results. And in this section, we're going to talk a little bit about really basic benchmarking, which is a really useful if you're going to be using HPC systems. Actually, this sort of basic getting on and doing a few things to explore how well it works for your systems and estimating resources is a really useful thing to do. As one of the first things you do when you get onto a system. So we're going to carry on using the sharpen example code and try and look at how its performance varies as we change the number of cores or the number of processes we're using for it. And the reason we're doing this rather than say memory or wall time or these sort of things is typically when you go onto HPC systems, the things you're charged against is the amount of CPU resource you use. Okay, so the number of nodes for how long is generally how the charging works. And I've got to talk about a couple of concepts there, parallel concepts, which is strong scaling and weak scaling. You may have come across these before, you may not have, but generally in HPC, people make a distinction between strong scaling and weak scaling. So strong scaling is where we keep the problem size the same, and then we try to use more cores to solve the problem faster. Okay, and weak scaling is where the problem size increases at the same rate as we increase the core count. So we're using more cores, but we're solving a larger problem. So generally, the amount of work per core continues to be the same as the weak scaling problem increases. Both of these approaches are equally valid uses of HPC. Typically a weak scaling one might be actually something that looks like a trivial parallel parameter sweep. We've got 1,000 images to look at. We've got 1,000 images to analyze. We could use one core. Say each image takes an hour to look at. We could use one core for 1,000 hours, or we could quite just as easily maybe use 1,000 cores for 1 hour to treat the problem. But if we wanted to increase the performance of the analysis of each of the images themselves, which is currently a serial process and takes 1 hour, then we might have to use strong scaling to do that. Try and use more cores to reduce the amount of time it takes to analyze each individual image. Okay, and in our case here, we're going to look at the strong scaling because we're going to look at how the time taken to analyze the fuzzy image varies as we change the number of cores. So we've already had a brief look at this because we ran it with 16, and then you wrote a script to run it with 128 cores, and we noticed that it ran faster. But we're going to do this in a bit more detail here. Both of these are perfectly valid approaches. Strong scaling is typically harder to achieve, and you have to put more work in terms of designing algorithms and writing your programs to achieve good strong scaling. But that's not to say it isn't hard to achieve good weak scaling for particular problems too. Okay, the two things are both valid approaches and can both be difficult. One thing that's useful to note also when we're doing benchmark is a couple of terms are program. That's actually the computer program we're executing. This is the sharpen MPI.x example, and the application is the combination of the program and the input parameters, because actually the scaling generally changes and depends on what input you're putting into the program, as well as the program itself and the algorithms it uses. So you've seen this before. We have the module load training sharpen, and then you can copy the data across. If you want to just build on the script we already had, so let me go to my work directory, which was called run sharpen. What this actually did was copy across the input data as part of the job script. That's perfectly fine. You can just reuse the script and build on it. So in the example here, we load the module interactively and then copy the image across manually, and then we can just run it over and over again. But keeping the script where it copies across the image as part of the script is fine too. It's up to you which approach you want to take there. That's fine. Before we start benchmarking or looking at performance and trying to estimate how much resources and what the best way to use those resources is, we need some sort of baseline performance number, some sort of thing to measure our improvement or lack of improvement against. And usually you choose the baseline as the minimum number of cores or nodes you can run on. For different problems, this might not be, for this problem, which is small, we can actually just run it in serial to get our baseline. So we can run with a single core, single MPI process. For many HPC cases, you can't do this because either it takes too much memory to run on a serial code, or it takes too long. So it's prohibitively expensive to do that. So your baseline may be, say, on one full node or two full nodes, or even if it's a really large problem, 1,000 full nodes. It's the smallest number you can reasonably run. For example, your example line is the best place to start with your baseline. In terms of actual pragmatism, when you get on an HPC system, because of runtime, you don't want to spend 24 hours producing a baseline. So you may choose to use more cores to get your baseline out than you would normally use for a formal benchmarking approach, but that is still useful in assessing what the best way to go about using resources on. So the first thing you're going to do is run the sharpen example. You've got a script that we wrote before, modify that so it just runs on a single core, okay, on a single node, and gets out the base performance. Look at the output from the application, and it might be useful to have some pieces of paper around to write these numbers down on, but you want to have a look at the calculation performance and the overall runtime. So once you've done that, you'll see in there's a calculation time and overall runtime. They're the numbers you're looking for on the standard out. You can get estimates from the batch system on runtime, but they're not accurate enough to be of any use when you're benchmarking generally. So I'd sort of ignore the options of using SACT to get the runtime out, because it's not accurate enough to use for these sort of benchmark performances. Most applications will output some sort of runtime as part of their doing. If your application doesn't output runtimes, then you can use the SACCount approach, but we won't worry about that for this one. You can view the image if you want, if you're logged in the same way, but that's not interesting. Then, once you've got your baseline serial performance, then you're going to be trying to fill in a table like this by changing the number of cores you're using and looking at the overall runtime. Note that when you get to 256 cores, you need to specify 2 nodes rather than 1, because you don't want to use 256 cores on 1 node, because that's oversubscribing the number of actual cores there are, because there are only 128 cores on a node. So what you've got to try and do is fill in a table like this, the overall runtime and the calculation time you get from the output, and you can calculate the I/O time and the core seconds according to the instructions here. from that. So can I ask you all to have a go at that? If you're stuck or don't understand or have questions about it, please say in the chat or ask for help. One of the helpers or myself can come and help you with that, or I can try and answer the questions generally. But what we're trying to do is do 1, 2, 3, 4, 5, 6, 7, 8, 9 runs for each of you with the different core counts and recording these different things. And you may find it easier to have it in a spreadsheet like Excel or something like that to compute the IO time and the calculation core seconds manually. Okay. So we're just at around past now. So this hopefully should take around 15. Yeah. We can keep your results on ARCHER2 in Excel program, so it's easy to find. But that may be more difficult if you're using Excel because Excel doesn't work very well on ARCHER2. So it depends how you do it. But I'll give you 15 minutes and we'll see where people are up to after the 15 minutes, and then we'll have a review and look at the output data. If you finish that very quickly, there is also the understanding performance section, which you can move on to and have a think about as well. So that's an interesting question. Can you just loop through doing things? The answer is that's not as easy as you'd hope. I can show you a quick way of doing it that doesn't use job submission scripts. A quickish way of doing it which doesn't involve job submission scripts, but it is a bit fiddly otherwise. Give me a second, I'll just type some stuff. In fact, rather than me type, I will point you at some documentation from another course that shows how to do this, where we do benchmarking in more detail. Give me a second to find it. So essentially this section of this other course does exactly this, and it actually uses the sharpen example as well, so it's entirely analogous to this. So you end up with something that looks a bit like this, with some sort of script that can capture the arguments, and then using this sort of syntax to SBatch to be able to push the arguments into the script. So then you could do something like bash run benchmark, whatever options, number of cores, number of runs that you want. But you could have a look there for that. I'll put it in the Etherpad as well, but it is more complicated than you'd hope that such a thing would be. Okay, that's been about 15 minutes. So I'm sure you've all made progress, and as some people noted, you know, actually this is difficult to automate. So actually, almost the quickest way to do it when it's a small number of runs is to is to just update the script and run it manual, as you sort of saw me doing in the terminal. Was just to change the script, rerun, change the script, rerun, change the script, and rerun it again and again. With the only complication being that that when you got to the 256 core one, you'd need 2 nodes and 128 cores per node, rather than the one rather than just a single node to be able to run it that way. So once you've done all that, and as I said, you continue to have access, so you can go and do this on other days if you want. You'll hopefully end up with a table that looks something like this. So these are the overall run times, and these are the actual calculation times. They're both taken from the output. The I/O time is taken by subtracting the calculation time from the overall run time, and the calculation core seconds is that's the calculation time times the number of cores. Okay, and if we look at this, you can see the overall runtime goes down and down and down and down, and then sort of plateaus once you reach 1632 cores, something like that. It stops getting faster for the overall runtime, but the calculation time actually does continue to get faster as you go down, as you increase the number of cores. And the I/O time, which is this sort of static serial overhead at the start and end of the calculation, is the bit that just stays the same. It doesn't benefit from increasing the number of cores at all. So what you find is that the calculation core seconds are pretty steady over time. That's the actual amount of CPU time used. So it shows you that the parallelization is pretty efficient up to 32 cores here. And what this illustrates a bit is that actually the parallel performance of your program is driven by primarily what proportion of it's still serial. Okay, so in order to get good performance and good scaling up to high core count, you need to make it a lot of your program parallel. Now, sometimes that can be easy in terms of parameter sweeps or trivial parallelism, and sometimes that can be more difficult depending on what you're actually doing and what the algorithm looks like. And to actually understand this and get a sort of more quantitative understanding of what, because the way we're approaching this is, what's the right number of cores to run this application on? Remember, the application is the combination of the program and the input. What's an efficient choice here? Well, then we go and look at understanding this performance, and we look at we compute 3 things. One is the speed up. That's the ratio of the baseline runtime to the runtime at the specified core count. Okay. The ideal speed up, which is if it was perfect scaling, what speed up would you expect to see? So if you use twice as many cores, it should go twice as fast, for example. And the parallel efficiency, which is the percentage of the ideal speed up you actually obtain. Right? And these are the key sort of numerical metrics that you can use to try and understand it. So there was an exercise here to fill in the table again, and then use that to answer some questions. The 3 questions were: what's the core count where you get the most efficient resources, irrespective of runtime? What is the core count where you get the fastest solution, irrespective of efficiency? There's like 2 extremes of scaling there. What's the most efficient use of resources, and what's the fastest solution? And the one in between is what's the good core count choice for this application that balances time to solution efficiency, and why would you choose that option? So I'll quickly show you the data here. So this is the overall runtime. So the overall runtime of the application. This is the ideal speedup. The ideal speedup's actually super easy to calculate because we started with a serial application, so it's just equivalent to the core count. So on 2 cores, it should run twice as fast. On 4 cores, it should run 4 times as fast, so on and so forth. And then the actual speed that we see is, this baseline. It's the baseline divided by the runtime. Okay. So you can see for 2 cores, when we deploy 2 cores, the ideal speed up's 2, and we get 1.8 actual observed speed up, or 1.9 actually. So that's pretty close. Again, should be 4. It's about 3. Should be 8. 4.5. Okay, and we go up. And then by dividing, if we look at the ratio of the actual speed up to the ideal speed up, we then compute the parallel efficiency here as this ratio. So you can see it's about 94% there, 75%, 56%, 39%, so on and so forth. Answering the specific questions here. The core count we get most efficient amounts of resources is almost always using a single core and no parallelism, because you don't have any overheads then for parallelization, the extra steps that are used to exchange information between the two. So actually the most efficient thing to do is just not parallelize at all. Okay. But there may be other constraints, right? Running on a small number of cores, it'll take too long. You won't be able to get the answer. You don't have enough memory and to be able to run the problem you want on a single core count, all those sorts of things. So it may not be practical, but it will always be the most efficient if possible. The core count where we get the fastest solution, irrespective of efficiency, is actually up at 256 cores. So that's definitely the fastest time to solution. This is the lowest number here. The parallel efficiency is awful, right? You're only getting 4% of what you should get if it was perfect. But it is the fastest time to solution, and sometimes that's a valid choice, right? Because it's not very efficient use of resources, but if you need to get your answer very, very quickly, then that trumps the efficiency, the efficiency question. And then finally, what do you think is a good core count for this application to use? In this case, about 4 cores is probably a reasonable balance of efficiency versus speed up. Okay, so it obtains a parallel efficiency of around 75%. So it's over it's about 3 times as fast. 75% isn't bad. Generally, the best choice is one that delivers a good parallel efficiency with an acceptable time to solution. Note that acceptable time to solution depends on circumstances, and it's something an individual person has to assess. What is an acceptable time to solution for them? Good parallel efficiency is generally considered to be something that's 70% or greater, though many people actually are pretty happy with a parallel efficiency greater than 60%. But as we said, running with a worse parallel efficiency may be the way you want to go, depending on, which is the most important in terms of time to solution, in terms of resources. Yeah, so George, on ARCHER2, there is a wrinkle here that you're allocated a full node. So this example, this toy example doesn't work particularly well for ARCHER2 in particular, because you always have your minimum request is 128 cores. So in this case, you'd have to run say 32 copies in parallel on node, really, to make use of all the cores, a good parallel efficiency, right? So you do have to be careful of those sorts of things. But generally, the applications you'd run on a system such as this will scale much better, and generally scale much better anyway. So the methodology stays the same. You run at different core counts and you calculate the performance, and then assess the efficiency and see what it looks like from there. Okay, so the methodologies, even though this example, George is right, 4 cores is not a very good use of ARCHER2, because the other 124 will be empty and idle, and you'd still be charged for them in this case. Okay, but what we're going to try and show here is what you'd sort of do if you got on a new system, and we're trying to understand what the right amount of resources to use. And it'd be this sort of methodology is increase the core count, maybe with increasing the problem size if you've got a trivial power approach, or you're like treating lots of images at once, for example, or something like that, or to assess what the right choice is of the number of cores or number of nodes to use are. So you have to know in advance what your priorities are. Do you need the results as fast as possible? Are you happy to wait longer to get more research done for the amount of resource you've been allocated on the system? Another tip is use your real research application to benchmark. And then try and shorten the run so you can turn around your benchmarking runs in a short time scale. Ideally 10 to 30 minutes, and then use basic bench. But you can use a really basic approach and just sort of try running it on, say, 4 nodes, then half it, run it on 2 nodes, double it, run it on 8 nodes, and see what the difference is, and that can give you a good starting point to work from. So Cameron's asked, if you don't specify cores, will Archer presume 1 to 8? No, the default on Archer is 1. So Julian, that's not quite accurate, I don't think. So because you could see that if we did you can see that because if we do the if we modify the script and take out these two options, I'm pretty sure. Oh, let's see who's going to be right. It might be Julian actually. Let's see what it does. 4583. So it defaults to 1 core. Okay, if you don't specify any number of cores. Okay, so you need to say how many cores you want if you want to use more than 1 core. Fine. Okay, so we're just about at the end of the course. I've just got this one last section with sort of hints and tips at the end of the course for today anyway. And like I say, there is the option to ask more questions later on as well. And that's just about being a good citizen on the HPC system because it's a shared resource. So one of the major differences, like I say, between an HPC system and your laptop is generally on your laptop, you're the only user, whereas on an HPC system, there's lots of other users. And there are a few things to bear in mind that this changes how you behave. So one of the key ones is be kind to the login nodes, right? So most HPC systems, ARCHER2 included, will have mechanisms in place to try and stop users using too much resource on the login nodes, because actually that can affect what happens to other people who are also sharing the login node with you. You know, if you use CPU intensive stuff, even though it's got 256 cores, it can become overloaded and run slowly for other people, or you're using too much memory and things like that. Now, there's usually automated things in place to try and stop people doing that, but you can't catch everything, and there is a responsibility on individual users to behave properly on the login nodes. Give me a second, sorry, my daughter's come back and making lots of noise. I just need to close the door. Sorry about that, that was a bit distracting. So you have a responsibility to behave acceptably on the login nodes, you know. So they're the right place to launch jobs and maybe compile code and do some initial testing and building workflows and maybe even some lightweight analysis and things like that. So generally you should ask, I mean, if you're unsure about something, please just contact the service desk or your local sysadmin if you're not running on ARCHER2 and ask if, you know, is it okay to run this sort of thing? That's always fair enough, and you know, you'll get a friendly, polite answer to that sort of thing. But you know, you could look at things like this, and you know, it's pretty common sense, right? So you've got a command that looks like Python physicssim.py. That doesn't look like it's going to be particularly appropriate because it looks like you're running a model or a simulation, physics simulation on the login nodes. That doesn't sound great. Make is a pretty standard tool for building software, so that sounds okay. Create directories.sh sounds okay as well. You know, it's just manipulating data and moving directories around. Molecular dynamics 2, it sounds like it might be something that you wouldn't want to run on the login node because it's a, you know, it sounds like an actual modeling program. And the tar, extracting a tar archive, absolutely, that's usually the sort of thing you do on a login node. Though if it's a really big tar archive, you might want to run it in the batch system anyway. You know, usually if you do something wrong, what will happen is that your processes will get killed by the local system administrators, and you might get an email from the service desk asking, say, we noticed you were running this. Please, can you do that in a different way or launch it on a compute node? But it is worth thinking before you act on the login nodes, particularly if you're worried that something may or may not be too large. The other tip I would have is test before scaling. So, you know, quite often people get onto a new HPC system and there's suddenly think, oh, I've got 2,000, you know, I can run a job that takes 2,000 nodes or 2,000 cores. This is great. Let's get going with the research. And quite often I've done it myself, you know, so you know, everybody's susceptible to, you know, these sorts of problems. Is you set a script going that either fails, you know, waits in the queue for 2 days and then fails because of a silly typo in the script, which is frustrating, or worse, waits in the queue for 2 days, uses up lots of resources, and then hangs doing nothing for the 24 hours you submitted for, which is both really annoying and frustrating and wastes a lot of your computer time that you've been granted. So, you know, what I would always say is write a small test version of your script and submit it to either at a smaller scale or to the test and development queues. Almost all HPC systems have some sort of way of testing. On ARCHER2, for example, there's the short QoS, where you can run quick tests and get fast turnaround to see if your script's fine, if the program launches fine, and then you can take that and scale it up. But before, this is compounded, obviously. Somebody was asking you, can you write a loop to automate submission of jobs with different sizes? And I put the link in there. These sorts of things become even more important. If you have some sort of automated loop like that, it becomes very, very simple to spawn 1,000 jobs that all use lots of computing time and do nothing useful, right? So if you're using these sorts of and building an automated framework to submit jobs, really be very careful with testing it before you go into production, because it's so easy to waste huge amounts of resources that way, and that's very frustrating, primarily for you. I mean, it's frustrating for the users who can't get access to resources, but you've burnt up all your computing time and wasted a lot of time waiting for these things to finish. Have a backup plan. Although some file systems are backed up, often just for disaster recovery purposes rather than recovering accidental lost files, your data is primarily your responsibility. And you should be aware of what is backed up and what isn't on an HPC system you're using. For example, on ARCHER2, the home file system is backed up, and if you delete a file by accident, you can go and get it back, usually. But on the work file system, there's no backups whatsoever. So anything you delete there is gone for good. George mentioned earlier that there was a way to alias the RM command to move things into a recycle bin. That may be a thing you want to do, but of course that has the downside that the user continues to use up disk space even when you've deleted files, so you have to clear it up periodically. But if you're producing large amounts of data, you need to have a plan for getting it off the system before your project ends. These things need to be thought about at the start of the project rather than at the end, rather than generating 5 petabytes of data and then suddenly worrying about where am I going to put this? And the Archer sysadmins are like, well, that's the end of your project. You've got 3 months. And you're suddenly like, well, I don't have anywhere to put my data. How am I going to transfer it all off? There's not enough actual physical time left to get the useful data off the system. So have backup plans, have data management plans before you start using the system, how you're going to get your data off, where you're going to keep it, and make sure that anything critical is backed up so that you don't have to repeat months and months of work just because there was a failure on the work file system that has no backups that you have no control over. Transferring data, we talked a bit about this in the transferring data section. When you're transferring the data, there's lots of there's different considerations for different things. We talked about archiving and combining into one large file. There's different components that have different bandwidths. So network speed, I mentioned that transferring over Wi-Fi from your laptop can be very difficult when there's large amounts of data, and it can be a right pain if you have to do that twice from one system to your laptop, then back up to another HPC system. We talked about firewalls as well, and there's various different ways to transfer data. Here's some example commands. Say you've got a data folder with 10,000 files, some large and small ASCII binary data, so it's like the worst possible mix of data you could possibly have. You could use SCP, you could use rsync -RA, rsync -RAZ. We could tar it up first into an archive and then use rsync to copy that across, or we could tar it up into a compressed archive and then use rsync to transfer it across. There's some pros and cons to all of these. So this one probably works, but it's probably very inefficient. 10,000 files take a long time. This will work in a similar way, preserves file creation times, which maybe may or may not be useful to you. This adds some bandwidth, adds compression, which might save you some bandwidth, but actually you're going to compress each of those 10,000 files on the fly. So that sounds like it's going to be gated on the CPU performance at the two ends rather than the network performance. So it doesn't sound ideal to me. This one looks more promising because we're creating an archive, so we're turning it into just one single file we're transferring. That's good. We compress it on the fly and uncompress it on the fly. Well, yeah, okay, that might well work and might be fine, but it pushes the time into the data transfer, and there's more chance of something happening and going wrong during the data transfer, which would be a pain in the neck. But if we could do the compression first, and then do the transfer without compression, then actually this is the best thing here, because this is going to make the rsync command as short as possible and have the least chance of failing as possible. Okay, so there's a few tips there around using HPC systems, around data transfer, backup and data management plans, testing before you scale up, and being a responsible user of the shared login nodes. I'm aware I've run a few minutes over, so I'm going to stop here. I will stick around for a bit, so if you've got questions or anything we've covered in the is unclear to you, then please do ask them. Like I say, we'll have a session in a couple of weeks also where you can come back and ask any questions that have occurred since you've done the course, and since you've thought about things and digested things and maybe had more of a play around on ARCHER2 with either your own code or with the examples from this course. All these lectures are recorded. They'll be processed and put up on the website, so you can always revisit them. The material will stay live as well in perpetuity, as long as GitHub Pages is there. So you can always go back and access that as well. Yeah, I really hope you found it useful. We'll also send out some feedback. Please fill in the feedback and give us feedback, both good and bad, because that's how we improve and make ourselves better. And it's really valuable to us how you find the course, and things you found good and things you found bad, things we can do better. It's really important to us. So it'd be great if you could fill in the feedback. Thanks for your questions. They've been really interesting. And it's so much easier when, and it's so much better having these sorts of interactions. So you guys have been great. And like I say, if you have any questions, either contact the service desk, contact me directly. My email's on the course website. I'm happy to try and answer them. Otherwise, maybe I'll see some of you in a couple of weeks if you have more questions. Actually, and I should say a super big thanks to all my helpers, Julian, Eleanor, and George, who's now left, who these courses wouldn't work without them. So thank you all so much, and I hope you found it useful.